Okay, in this section you will need your ruler back, so if you don't have one, please go grab one. Otherwise, groupie member Amy was getting $10 per lap and started the walkathon with $40 in donations. Groupie member Denny was getting $20 per lap and did not get any donations. So question 1 says, after how many laps will they have made the same amount of money? Okay, so one way to look at this is go ahead and create a table. Fill out as many laps as possible in order to find out when that money made is going to be the same. So let's go ahead and look at Amy. After lap 1, it looks like Amy has made $50. After lap 2, she has made an extra $10. And again, that's going to be our pattern. We're just going to add on $10 per lap. Looking at Denny, he is only getting $20 per lap. He didn't get any donations. So after lap 1, he's at his $20. And then we're just going to add on $20 per lap. And look at that. That's when we stop, because after those 4 laps, it looks like they have made the same amount of money. So question 1, after how many laps? 4 laps. Okay. Looking at question 2, find a color I haven't used here. Question 2 says, how much money do they both have after walking this lap? Well, according to our table, they both have $80. Okay. One way that we can solve that problem. 3 says we're supposed to write equations that represent this. So this is just a nice review of writing equations, dealing with laps and amount earned. So dealing with L's and A's. We know that for Amy, Amy's amount is $10 per lap plus the $40 in donations. We know that Denny's amount is just the $20 per lap. So looking at these, good review of vocab. Denny's is called a proportional relationship because the amount of money earned is directly proportional to how many laps. Amy's is non-proportional because we have that y-intercept. Okay, even more review, we're supposed to graph these equations. So we're looking at laps and amount earned. Looks like we can probably go by 1s per laps and go by 10s for amount earned. Okay, that's really messy down here. I want to fix that. Knowing that this is laps. And this is where our ruler comes into play because we are going to need these to be nice straight lines. Okay, review of graphing. Remember, this is in slope-intercept form. So we start with that intercept, and we know that Amy had that $40 to start with. And we know after that, she got $10 per lap that she walked. So go ahead and draw as straight line as possible. It's fun for me on a computer, but bear with me. That's not too bad. With mess all over the place. Okay, remember that Denny's is going to be a little bit different because his is not proportional. So he is going to start at 0, 0. He receives no money in donations, but he is going up $20 per every lap that he is walking. So again, nice straight line with ruler. And that didn't really work for me. Okay, question 5 asks where do they intersect? So looking at your graph, go ahead and see where they intersect. Give me just a second to fix mine. Okay, I apologize. Writing on glass is kind of weird, but this is where they should intersect. Looking at the intersection of this right here. Okay, well, what is that point? That is the point for 80, which is interesting because look at what we had up here. What does that intersection mean? That means after 4 laps, they both have $80. Okay, so we can actually solve this by graphing both and finding the intersection. This is called a system of equations. Since we have 2 of them, it's a system. We can look at them, we can compare them and graph them to find that one solution that works for both of them. Notice in this situation, that is the only point that they share. They go off in separate ways. And most of the time, that's what we're going to see in a solution of equations, that they share that one point together. So that's what we're going to look at in this section. Go ahead and get out the notes and vocab. Okay, the objective of this section is to solve a system of linear equations by graphing. And they do have another good example here. It says the income from the CDs sold can be modeled by that equation, y equals 10x. Y represents the total income of selling the CDs, x is the number of CDs sold, so they must be selling them for $10 each. And then looking down here, they look at the 4x plus the 1500, which was their other part of their problem. They graphed those together and we can see that as a system of equations. I did kind of just briefly go through that because, again, we saw a good example in our introduction. But understanding that those 2 equations that we used were called a system of equations. That ordered pair that is a solution of both is called the solution of the system. So those are the 2 vocab words that we're looking at. A system of 2 linear equations can have the one solution, which we had. At 4 laps, they had $80. Sometimes they can have an infinite number of solutions, and sometimes they can have no solutions. And I'm not going to read through those definitions because they do a good job of showing them here in this nice little graphic organizer. The number of solutions of exactly 1, which is what most of the time we're going to see, is consistent because we do have a solution, but it's also independent because those lines are independent of themselves. One is going one way, one is going the other. This one, if you notice, there's only one graph there. So sometimes we actually have 2 equations that form the same line. Many times one equation is written in slope-intercept, the other's in standard form, but they are the same equation. That is called consistent because we do have solutions. We just happen to have an infinite amount of them. But it is dependent because that line is the same line. It's dependent on itself. Sometimes we have no solution. Notice these 2 lines. Notice something about them. They're parallel. Parallel lines never intersect, which means that we're not going to have a solution to that, which is called inconsistent because we have no solution. So I would recommend keeping that little graphic organizer out so you can work on it with this next example. So example 1 says we're supposed to use the graph at the right to determine whether each system is consistent or inconsistent and if it's independent or dependent. So back to review of graphing. You'll have to bear with me with this computer, but remember that plus 3 means we have a y-intercept at 3. Slope, I'm going to put over a 1 because I know from that 3 I'm going to go down 2 and to the right 1. And there's my first graph. Way off a little bit better. All right, 1 graph done. Curve. Now let's look at the second graph. We have a -5, which means that my y-intercept is down here at -5. This is always a weird slope right here because there's nothing out front. Do put a 1 over 1 there because we know that that is a slope of 1, that from that point we go up 1 over 1. And there's our other graph. All right, now we have to go back to what they're asking us to do. We're just supposed to look at the vocab of this. Which one of the 3 is this? Well, we received 1 solution. So if we look at that, remember it's consistent because we got a solution, and it's independent because they are both different graphs. So answer to this, we are going to call this consistent and independent. They didn't tell us to actually solve it. They just wanted to tell us what type of solution are we going to get. We could have actually just looked at those graphs and looked straight at that slope, because if they have two different slopes and they're both written in slope-intercept form, we know it's going to be consistent and independent, because we know that they're only going to have that one value together. So looking at B, I'm going to kind of predict the future here and say, whoa, we have two of the same slope. I know that that means these two are going to be parallel. So I'm guessing we're going to have no solution. So let's go ahead and try it out. -5 is down here. Slope of down 2 and over 1. And I'm going to graph this, guy, as good as possible. And then graph number 2, we have a y-intercept of 3. We have a slope of down 2 and over 1. So using my knowledge of slope-intercept form and slopes and parallel lines, I realize, even though my graphs are kind of ugly, they are parallel. It kind of looks like they're going to intersect down here, but they won't. They should be parallel. So no solution here. What was that called? That was called inconsistent, because we will receive no solution. All right. Go ahead and try that with 1A, 1B. Again, graph these, and we're just looking at that new vocab and what they mean. Okay, many times these are going to be our answers, consistent and independent type of answers. But realize that that's just the vocab of it. Now we actually want to figure out what that point is. So one method of solving a system of equations is to graph the equations carefully on the same coordinate grid and find their point of intersection. Again, this is the point. This point is the solution of the system. So that's what we're going to do carefully with our rulers. Graph each system and determine the number of solutions that it has. If it has one solution, we're supposed to name it. So looking at this, we have an intercept way up here at 10. From there, we go down 3 and over 1. So there's our first equation. Graphing that as good as possible. And then our second equation, looks like we went down 2. Remember that slope means that we have a 1 over 1 slope. So from there we go up 1 and over 1, and we graph that as careful as possible. Okay, and this is kind of the drawback of using graphing to solve these systems, because look where mine intersected. It intersected halfway through a point. So I'm not quite sure where that is. So it might be 3, 1, it might be 4, 1. And that's where I'm going to show you how to graph this on a graphing calculator to double check and make sure. So go ahead and get out your graphing calculator. Okay, so I'm going to write the steps on how to put this in the calculator, and then we'll go through how to do that. So the first thing you do is there's a y equals button. You're going to hit that, and in y1, you're going to put the -3. I got a cheat here. And there's an x t weird button that looks like this, and I'll explain that, plus 10. In the y2, you're going to write your x. You're going to hit that one button, -2. After that, we're going to hit the second button, and we're going to say trace, and we're going to find the intersection. And then we're going to hit enter 3 different times. Okay, so with that in mind, let's go ahead and try this. So calculator out. The y equals button is right here. So in y1, here's my -3. Here is that xt theta button that represents a variable. And then I'm going to add 10. Then I'm going to arrow down to x2 or y2, and I'm going to say x, and I'm going to subtract 2. Don't put a negative in there. Okay, I have my two equations. I don't have to say that. It knows that. So here's my second button. Here's my trace button. So second trace. I want to find the intersect, which is 5. So gives me my two graphs. Notice where it says first curve. A lot of times equations aren't linear, so they think that maybe it's a curve. So we're going to hit enter because we know that it's on our first equation. Then it says second curve question mark. We're going to hit enter again because we know that it jumped down to our second equation. Then we're going to hit enter and it says guess. Sometimes you can guess. Other times we just say no thank you and we hit enter again. And look at that. They give me the intersection at 3, 1. So I do know that I'm a little bit off here, but my intersection should be at 3, 1. Okay, so again, we graphed each equation. We asked the calculator, please tell me where these two equations intersect. We told it which line we were looking at, which line we were looking at. We kind of skipped the guess, and then it tells us exactly where the point is. So what is the solution of this? The solution is 3, 1. Okay, so good stuff with that, with using that calculator. The only problem is, look at this calculator one more time. When we do y equal, it's only written in slope-intercept form. So when we look at b, we kind of have some problems because these are both in standard form. So let's go ahead and graph them and see what happens. All right, standard form. We know that this is where we can do our cover and solve. So I'm going to cover and solve this, and I see that x equals a -1/2. Okay, so I know x equals -1/2, 1/2. Which is right here. And then covering and solving, I know that my y equals a +1. So kind of tiny points together. So let's go ahead and graph those. As good as possible. And we're going to try that for this next one. Again, standard form, so we know that we're going to cover and solve. I see that x equals 6/4 or 3/2, which is 1/2. So x equals 1/2. And there's another problem dealing with fractions. Sometimes it's kind of hard. Covering and solve here, I know that y equals a -3. So -3. Graphing these two, I should realize something, that even though my graphs are kind of ugly, looks like these are parallel lines. Okay, to be completely sure, I would have to write these both in slope-intercept form to see that, but visually I see that these are parallel. So what's my solution? No solution. They are not going to intersect, so there is no point that these two graphs have in common. Okay, so go ahead and kind of play around with your calculator and see if you can put these in your calculator. As a hint, 2a, well, both of 2a and half of 2b are written in standard form. So if you do want to put this in your calculator, you're going to have to solve for that y in order to do that. Go ahead and try it, and I'll put up the answers. Okay, let's go ahead and look at 2a. I went ahead and put them both into slope-intercept because I knew I was going to use my calculator to double check this. So I ended up with x minus 2 and -2/3 x plus 3. Graphing them, it does look pretty darn close right here at 3, 1. But I went ahead and checked it. Again, I went to that y equals. I plugged them both in. I went to that second trace intersect, enter, enter, enter. And yes, they do say that it intersects at the point 3, 1. That is the point that they share. Looking at 2b, the first one already was in slope-intercept, so I moved around the second one, and look at what I noticed. This equation, written in standard form when translated into slope-intercept, is the exact same equation. So all I had to do was graph it one time, and say that these two equations share an infinite many amount of solutions. So answer on this one is that sometimes 5% of the time where we are going to have an infinite amount of solutions because they share every single point together. All right, last one, looking at story problems. Again, we can use this to look at story problems. It says that the number of girls participating in high school soccer and track and field has steadily increased over the past few years. Use the information in the table to predict the approximate year when the number of girls participating in these two sports will be the same. So let's look at this. Soccer. The number of girls participating in 2008 was 345,000. Average rate is 8,000 per year. So look at this. This is my y-intercept because that's where I started in 2008. This is my slope because that's how much I'm increasing per year. So I'm going to go ahead and just write these as y equals. I know that I have 8 per year plus 345 for soccer. Track and field, I'm still going to use these as my y-intercepts and my slopes. But this is 3 per year, but we started with 458. Okay, notice how this is going to be a little bit more difficult to use this graph. So we are going to use the graphing calculator. Not even going to try this. Because we're going to, as easy as that sounds, we are going to have to look at what happens when we have these big numbers in there. So go ahead and get your graphing calculator out. You can hit that clear button or the second and then quit to get out of this. One thing that we want to mess around with to show you how this works is this window button, because when we look at a graph, if you hit this window, this is what I call the default. It's usually an x min of negative 10, x max of 10. Y min of negative 10, Y max of 10. These X scales and Y scales, that's just what each tick mark represents. So sometimes, you know, we change that to 10s and 2s. Here we just kept it at 1. Well, let's go ahead and look at this. We are looking at number of years, which deals with our X value. So we might maybe want to change that to possibly 20 years. Another thing, we don't usually have a negative. When we're dealing with story problems, we don't usually have negatives. I, however, keep those in there just as a cushion so we can at least see a little bit of the outsides of our graph. It's the Y max that we're going to have a problem with because look at these numbers that we're dealing with. Definitely bigger than 100. Okay, or I'm sorry, definitely bigger than 10. So what are we going to change it to? Well, we know that it's going to definitely be increased more than that. So we don't want to set it at 458 because we know it's going to be bigger than that. So why don't we go big and set it at 1,000? Again, keep that negative 10 just as kind of a cushion. All right, with that in mind, we do have our window set up, which you do need to keep in mind when you're dealing with story problems with numbers this big. Now I think we should be able to go ahead and graph it. So I'm going to go back to my y equals, knowing that if I hit this clear button, that's going to get rid of all my other graphs. I'm going to plug in 8 with my x plus 345. I'm going to go down to my 3x plus 458. And one thing I didn't show you before, you can go ahead and hit this graph button so we can see those two graphs. Okay, kind of hard to see, but it looks like they're going to intersect somewhere over here. These don't show us very nicely what that is, so we're going to hit our second trace and we're going to ask it to find that intersection for us. Again, first curve, that just means that's the first line we're going to compare. That's the second line we're going to compare. Hit enter one more time. No thanks, I'm not going to guess. And go ahead and hit enter. And here's our problem. It's bigger than 1,000. So we're going to have to go back to this window, second quit. We're going to have to make things bigger. So let's go big. We might as well even try 40 years. And we might as well try 2,000. There's no such thing as too big, but too small is what's going to happen right there. So now let's graph it. Now we can see that it intersects right there. So they should, if we go back to second trace, it should give us the right one. So there's our first curve. There's our second curve. No, thank you for guessing. There it is right there. So intersection at 22.6 and 525.8. So I'm going to write that down before I forget it. 22.6. And of course I forgot it. Terrible memory. 525.8. 525.8. Okay, very nice that we got a point there, but we have to understand what that means. So use this information to predict the approximate year when the number of girls participating in these two sports will be the same. Well, 22.6 is about 22 years. So 22 years after 2008, or we're going to say 2030, there will be about 525,000 girls participating in both. Okay, calculators are great to use in these type of problems, but again, if you get that sign change, and I did that on purpose to show you what that means, that doesn't mean there's no solution. That just means our window's too small. So open it up a little bit. Problem solve with what you're going to do with that window. Understanding what X means and understanding what Y means really does help out there. Okay, go ahead and do that with 3. Our numbers are a little bit easier, but if you want to go ahead and skip this graph and go straight to the calculator, that's fine as well. Okay, so I set up 2 equations that Joe has $10 per week plus the 14 he already saved. Josh has $7 per week plus the 26 he already saved. I tried to be smart here and put my little break in my graph, which means that I'm missing some values here to start with 14 because I know that that was the smallest number, and graph from there so I could see the intersection, but look at that. That didn't even help me. Intersection is off the charts. So I had to go to my calculator. I did go to my window right away because I know that it doesn't go back to default. It stays with the window that you already had, which we had what, 2000 in here? So I changed that. I did keep the 40 because I don't know how long it's going to take them, but I changed my Ymax to be around 300. I went ahead and graphed that, and I realized maybe my graph is a little bit too big because my intersection's down here somewhere, but really that doesn't matter. Ugly to see here, but if we go to that second trace, ask it to find that intersection, there's my first point, or that my first graph, my first equation, my second equation, and guess, they tell me intersection is at 4 and 54. So in this situation, what does that mean? That means in 4 weeks, each boy will have $54. One comment, when you go to that second trace and it says first curve and second curve, you don't have to worry about where those points are. If you only have 2 lines in there, it's going to jump from one line to the other line. Even if you can't tell that, you know that it's going to do that. Okay, so graphing calculators in this situation can be a lifesaver as long as you know how to use them. So with that in mind, keep that ruler out though, because I do want you to at least review how to graph these and start working on the assignment for this section.